So does locally mean using only one chart, and globally is phi1 and phi2 together?
No, locally means that if the chart were to be able to cover all of the S2, we see it cannot. There is one point it cannot cover. Okay. So for example, chart number 1 cannot cover the North Pole, right? Chart number 2 cannot cover the South Pole, right? So that's what it means for it to be local.
If it was global, then all points would be covered.
Right, yeah, yeah. I mean, that is also possible, right? A trivial example is Rn. Rn can be globally covered by Rn. And there are non-compact manifolds where you can do that. You can cover the whole manifold by one chart. It's just the metric that is different. It's a notion of difference, and the notion of distance that changes between that manifold and Rn. So for example, you know, the distance on this manifold, right? So the distance on this manifold is not preserved under this projection, right? And that's why, you know, when we look at an atlas of the world, we see that a lot of the maps there are all these, you know, distortions, right? You know, Russia looks huge, and that's because they're using a projection where, you know, those parts of the world, the northern and the southern parts of the world, they look huge. So they're probably using a projection where, you know, you have the globe, and there is some, you know, axis which goes through here, and what they're doing is that they are covering, they are taking a piece of paper, Rn, and what they're doing is that they are just wrapping that Rn like that, and then they are, you know, projecting from the center outwards, right? Of course, this does not cover the North Pole and the South Pole, right? So you know, or, you know, depending on how what the length of this you know, paper is, it doesn't cover, you know, some part of the Arctic and the Antarctic, and that's why in a lot of world maps you don't have the full Antarctica. You just have Antarctica kind of, you know, just like a, you know, showing up a little bit. And then you have a different, you know, picture of Antarctica. And for that, what they do is that they just do the stereographic projection from the North Pole. Okay, so no single chart cannot cover the whole of S2, and that is a theorem. Okay, so a collection of charts that cover a whole manifold, that chart is called an atlas. Okay, so phi1 and phi2, this set together, we call that, say, big phi. So these are charts, and this is what we call an atlas. Okay.
There are charts just some plane or some topological object.
Yeah, chart is essentially a projection onto some subset of Rn. So, you know, so here, this is a chart, right? I mean, this is a chart. This is a chart, this plane. And the fact that we are mapping every point from the sphere onto this plane, that's a chart. The top part is another chart. And the fact that we are mapping all the points on the sphere except the South Pole onto this plane. So phi1 and phi2, these are the charts. And the collection of those charts that cover the whole S2, that is what we are calling an atlas.
Sir, you mentioned on the non-compact thing, like the volume is infinite.
Right, yeah,
And
but you know,
And on the 2D surface, the volume is like just an area.
You mean this one?
Yes, sir. Like if this is a non-compact, like the volume area is infinite, and which is generalized with the term volume.
Right. So, okay, that's a very good point. So the sphere obviously has finite volume, right? Finite surface, sorry, surface area, right? Is that clear to everyone?
Yes, sir.
Yeah, but what we are doing is that we are projecting onto this plane, and on this plane, obviously the area of the plane is infinite. And if you're just excluding one point, which is some big circle at infinity, we can see that the area of R2 is infinite. So how do we reconcile with the fact that under the projection, a finite area surface gets projected onto an infinite area surface, right? Is that the question, or is that the idea you're yeah?
Sir, I mean, what about disconnected balance? You can repeat again from the beginning. Again, from the back.
So, sorry?
Yeah, you can repeat the question.
Sorry, what is the question?
I said, can you repeat a bit? Repeat because I'm getting disconnected.
Yes, sir. The question
Okay, so what Farhan is asking is that we are talking about finite compact manifolds and non-compact manifolds, and S2 is a compact manifold, right? Because it has area. S2 is a two-dimensional surface, so it's what we call volume is essentially its area, right? Its surface area, because the inside of the sphere is not part of the sphere, so we are ignoring that. So we are not talking about volume here. We're talking about so the surface of S2 is finite, right? But under this projection, we see that we are projecting the sphere onto a two-dimensional surface which has infinite area. So does this mean that somehow S2 has infinite area and that it is actually a non-compact manifold? So I think that is the kind of the heart of the question that Farhan is trying to raise.
Yes, sir.
Yeah. So yeah. So that's a very good question, and the idea is that the chart that we use to represent a compact manifold is a representation. Okay, it is not the manifold itself. So when we are discussing the area or the volume of a manifold, we actually have to do an integration over the manifold, right? But if we do want to use the coordinates on the chart, then we are taking R2, but the measure of distance on R2 is different, right? So for example, the point from the North Pole to P here, the point P, the distance, there is some arc length, which is the shorter distance, right? Shortest distance. Okay. And it's obvious that if we, but the distance from this point to the North Pole on the surface is infinite, because the North Pole is infinite far away. It's actually not part of R2. So that's a very, very easy example to see that distances are not, let me write that down, distances are not preserved under projections. Sorry? Sorry, can you repeat that?
I think you wasn't
I think I probably was. It's probably your connection. Were people able to hear me?
Yes.
Hello?
Yes,
Yeah,
Current
I think,
is
I
disconnected.
think, yeah, I think Proma, was it Proma or Sitima who was talking?
It was Brahma.
Okay, Proma, I think your connection is a little bit choppy. One thing you can do is that, maybe tomorrow when I post this lecture, you can listen to it again. But I'm happy to repeat, okay? And that's why I'm writing things down. And the first comment is that distances are not preserved under this projection. Now, distance squared is essentially what we call locally an area, right? So areas are also not preserved. Okay. Many areas under the natural. So R2 has a natural, let me show you. Okay. So R2, has a natural metric, right? The Euclidean metric. So that means that distances in R2, if say A and B are points in R2, sorry, A is X and Y, and B is X prime and Y prime. Then in R2, there is a natural notion of distance between these 2 points. So these are points, not vectors. Then, we can measure a distance between A and B. So we call it delta, let's call it, say, delta AB. And this is X minus X prime squared plus Y minus Y prime squared. Okay, so this is the notion of distance, natural notion of distance, the one that we use in Pythagoras' theorem, right? So, and then there's also a natural measure, you can extend this idea to a natural, measure of volume. Okay, so, and if you're using, say, a Cartesian coordinates on R2, natural measure of volume on R2, right? So if you're using, a natural measure of R2, then the area, unit of area, let's call it dA, is just dx dy, with the limit that x and y go from plus infinity to minus infinity, right? So the important point to note is that neither of these things are preserved under this projection. Okay, so if I project over here, this point, this is the distance. Here the distance is much greater, right?
Yes, sir.
So basically, if you want to measure some volume, say some parts of some, the volume, say if you want to say what is the area of this part of say S2, but you want to calculate in terms of the projected stuff down here, you have to use a different metric. You cannot use a natural metric on R2. You have to use a different metric on R2. Okay, in that metric we can work out, if you want, a measure of distance, and that measure of distance will give you a different measure of volume. So we cannot think of R2 as we have to think of R2 or an open set of R2 with that particular metric. And in that metric, the volume will be the same. Okay, so which is the same thing as, and that's what we do when we, when we do the area, when we integrate the area and we find, d theta, d phi, and all that on a two sphere, we're actually implicitly doing all of that.
Sir, you mentioned Minkowski metric. Is that like some other formula regarding x, y, z, and t?
Yeah, so the R4, for example, that's a four-dimensional Euclidean space, and the natural metric on that is is going to be, say, if there are 2 points, say A and B. So A is, say, T, X, Y, and Z, and B is T prime, X prime, Y prime, Z prime. Then the Euclidean metric, let's call it delta AB Euclidean, that is going to be the square root of T minus T prime squared plus X minus X prime squared plus Y minus Y prime squared plus Z minus Z prime squared, right? So this is what the Euclidean metric is. But on R4, and we can do it on R2 if you wanted to, the Minkowski metric, is, let's call it, it's going to be, and it's better if I use the squared here. And here I can just, for parity, I can just do square and get rid of the square root. This is going to be minus T in units where the speed of light is 1. This, so there's a minus sign here. And then plus X minus X prime squared plus Y minus Y prime squared plus Z minus Z prime squared. Okay. So this is the Minkowski metric, which is, we wrote it as eta mu nu, right? Whereas for the Euclidean case, the metric is just the identity matrix. Okay, Farhan? So these are differential geometry ideas. It's not really group theory where you should learn this, but it's good to get exposed to them informally at least.